So basically, on one chip, we can go up to maybe 11 or 12 qubits because of the 220 megabytes. But we are thinking about to combine different chips, connected to this high-speed connection. Okay, this is computer part. Because to solve the decomposition problem is hard enough, even at 10 qubits. It's a mess. It seems that we can do it now with our new results, but it's still an open research.
Okay, so thank you very much, Peter. And let's move to the next talk. Please, everyone.
Neither guy is very, very deeply in programming experience. He has mostly designed that
Do you know that? Azt tudom, csak arrébb akarom rakni a görbben. Who use Mac? Any Mac user can help us to make full screen.
Which program do you
View? Oh, okay. Yeah. Okay.
This is beautiful.
Yeah. Yeah. Okay. That's true.
Okay. Okay. It's the bottom is cut off though.
I don't know why. Or
maybe.
Okay.
Yes, there's a lot of it is cut off. Yeah. Too zoomed in. Oh, maybe it's a aspect ratio issue.
Yeah, I
Not full screen, but
Right.
or something maybe.
you are this one. There you go.
It's still cut off. We just fit the screen, not full screen, because I'm worried it's going to cut.
Of course. So that's all right.
Yeah, like this. Yeah, I like this.
Like this.
That's the wrong talk thing.
Oh. We're on the wrong talk.
Like that, but the right talk.
This one?
Yeah.
And there you go. And cutting.
Whatever you did for the last topic, yeah, like maybe.
Next. All right.
Yeah, perfect. Okay.
And then try.
Yes.
Voila.
Okay. Okay.
So let's pretend everything is all right now, I think.
Yeah.
Okay, so I'm Gregory Morris, and I was doing work on the FPGAs with Peter, who just spoke, and my PhD supervisor is Tomasz Kozik, and basically we were and we're basically doing a collaboration between the informatics department and the faculty of science. Peter's from the Department of Physics, I'm from the Department of Programming Languages, but we've been closely collaborating and doing some interesting research projects, including on the FPGA and the Groq chip. And I got very detailed into the Groq chip. And the motivation behind this, which we'll go through shortly, was trying to kind of look at using these high-level tools like Max Compiler. So using these high-level tools, could we do some, massive mathematical operations and get a good performance and get a good amount of resource usage? And it turns out that, for example, the floating point addition is more expensive than floating point multiplication. If you know the details involved, you'll understand why. But because of that, I was researching how to do one particular aspect that was quite inefficient if you just did some simple operations from Max Compiler. And so I ended up looking into these leading zero counters, and I found a research paper which did just that. And I decided that from looking at what they did, that they really were focusing on power. And it seems like that's generally the industry standard, but we're very much focused on high performance computing. We aren't as concerned about power. Power is kind of, it's an issue, but it's the lowest on the priority. For us, the resources and the concurrency effectively, and the performance are the number one issue. And they kind of go hand in hand, but resources specifically are a limiting factor. So you want high performance, but you want to maximize the usage. And so I looked into this topic and I found that the state-of-the-art paper on this, basically written by these Zahir et al., efficient leading zero implementations, they basically kind of missed the point here. They did come up with something that was minimizing the number of lookup tables in this little microscopic circuit and stuff. But then they went with a very modular framework, a very nice framework. And well, it turned out that they missed a key optimization, which basically would have no cost to it. And so I decided to just investigate this a little more to see if I could come up with something that would be more applicable if you really wanted to maximize the performance. So with floating point addition, basically the problem occurs when you have a subtraction, okay? And this doesn't mean a floating point subtraction instruction. This means that you're adding things with opposite signs, or you're subtracting things with the same sign, right? Okay, that context means that instead of when you're actually adding things with like signs or subtracting things with opposite signs, where you only have to check a few bit positions, this is a special case where there's a true subtraction occurring and it can underflow, and your mantissa, your result, needs to be shifted back up, your exponent adjusted, etc. And so you do a leading zero count, and this is obviously used in just about every floating point hardware in existence. And if you don't have this implemented efficiently, if, for example, you want to put thousands of floating point additions on your FPGA, well, you're not going to get anywhere because you're going to get limited at, maybe a few hundred or so. And you need, if you want state-of-the-art minimizing resources and yet maximizing performance, you have to look at things from a different perspective than maybe is the traditional perspective, which is power. So basically, we can go into the math a little bit, but you have, there's some, also some formula here where you can use the floating point even to effectively count the log base 2. So it can actually work as a leading zero counter. And this is kind of a little bit of a novelty or a hack. I went into a little of the math. It's not super important. But basically, you can see here too, just to give a more deeper highlight of the process, this is where you do it. So this is a good example of a kind of a good generic prototype. Of course, there's all sorts of details with this, and the proprietary implementations, they have short paths and long paths. They do all sorts of tricks, but in general, this is basically what it looks like. And you can see it's just this one little process here, which isn't even the most expensive, actually. If you really want to start dealing with the performance and the resource consumption, the most expensive operations will be right here. Your shift lefts and rights, okay, because bit shifting is very expensive when it's by an unknown amount, not a fixed amount. So here's an example from even the classic example from the bit twiddling hacks, where you can actually take the log base 2 using the floating point unit, and I guess the details aren't super important. I can explain all the little details here. I mean, if you're an expert on floating point arithmetic, you can figure it out, but they're doing some integer hacking of values into the float, and then they're just subtracting. So as far as the floating point unit goes, it's doing one floating point subtraction. So it's relatively efficient, right? But still, the floating point unit, you have to push on the stack, pop out the stack, but it's one subtraction. And so it subtracts the implicit bit to cause a leading 0 count, to cause the subtraction under float. And then it is able to do a log base 2. And actually, it's not the most there's tons of multiplexers, but we have these ones called a MUX F7 and a MUX F8, basically allowing you to use a lookup. Flip-flops. So the configure logic block has 8 flip-flops, not too important in this context, but it has these 4 lookup tables and it has these multiplexers that can be used. Okay. The lookup tables, however, are kind of interesting in the Xilinx architecture because they implement it like this. A LOOT6 is actually 2 lookup table 5s. And that's not too surprising. Any lookup table n could be, 2 lookup table n-1s with a multiplexer, but they give you the signal out here, which is a nice little flexible thing because it means you basically can have 2 LOOT5s with shared input, or you can use it as a LOOT6. And I don't know if you could do anything with this input in that context. Maybe you could find a clever case for that. I haven't seen one, but basically it works as either 2 LOOT5s with shared inputs or a LOOT6. There's many times where you want to take some bits and you want to AND them or them at the same time. And so this saves a lot of resources, saves a lot of wires. This is just a very clever architectural strategy that they've used for a very generic configurable logic block. And they call this a LOOT NM, and N is 6 and M is 2 here because it's the number of inputs is these 5 plus this one for the multiplexer, and the outputs is 2. Okay, and the MUX F7, I mean the multiplexers aren't too complicated. You have something that chooses whether it takes this one or this one. Okay, so you'll get these outputs, and then again the same thing with the MUX F7s can go into a MUX F8. So this would be the MUX F7 and then the MUX F8. And so basically you can actually do some extra multiplexing basically for free because you're staying within a configurable logic block. You don't have to go out of the logic block, go to other lookup tables. So again, for this high performance perspective, sometimes it's very useful to look at the actual architecture that you're using and try to come up with a solution. Okay, so the synthesis and implementation makes extra complications basically because though the synthesis translates VHDL into the logic elements, you have all this optimized design which is going to do its own heuristical stuff. You have placement, you have physical optimization, you have routing. You have some really key phases. The physical optimizations are optional, but they are the default. They're generally used for most of the strategies, and even these post route for some of the better strategies. And finally, you get a bit stream, and you can actually run your FPGA program. But we have to look at some of these phases like synthesis, optimization, placement, and post place, because if you want to be very careful, you have to actually adjust settings to make sure that it isn't going to take something that you want designed in a certain way and maybe duplicate things, maybe do things for optimizing it for timing when you want to save resources and making the wrong trade-offs. So then we have to put that underneath, and on top here is Max Compiler. And Max Compiler, this the data flow engine framework, which uses Java as the description of your program, and will translate it into VHDL and then call Vivado to synthesize and implement it. This one does have a few useful tools. It can disable and enable the automatic pipeline registers. So, for example, you might want your signal to go through a bunch of lookup tables before it stores in a register somewhere. Can be very good for getting high performance, and especially if your clock will allow. There's also the ability to just manually pipeline a symbol or a signal if you've disabled pipelining. There's also an ability to integrate custom intellectual property solutions, which kind of sounds like the direction I'm going in looking at it from such a low level. But okay, I need to move quicker. Okay, so we'll go that there's a couple directives, keep and don't touch, which help you preserve signals. And this is super important if you don't want Vivado to start shuffling your whole design around and doing what it thinks is best. And guess what? It's using heuristics. It doesn't have a mathematical solution to this problem, of course. The circuit SAT problem is NP complete. So basically the old method was doing it this way with a cascade. So you can see 3 loops going into this 4th loop. It's a cascade. They give this equations and well, these are the tables, but they also you can derive an equation very straightforward from that. And then they chain the 16-bit leading zero counter in a modular way by just chaining 2 8-bits together. What we came up with is that you can basically have a cleaner table, and then again, this is the logic formulas corresponding to it, but basically this is actually a much simpler table. I mean, you can see if they're all 0, you put all the signals as 1. It's kind of a special case where it means you don't care about the other outputs because you have a special all 0 signal. And then here is our 16-bit leading zero sign. And what we did is we decided that you could break it into this kind of 5-4-4 type strategy, a non-symmetrical and a non-modular strategy. And this is probably a bit much to just understand in a few minutes, but basically by not using a modular strategy, you're able to actually do this without cascading and thus making the path short. And so the formula is basically you're going to take these basic signals from the first stage, and then you're going to define the output of that stage, like the 16-bit stage. And at the 16-bit stage, then you can go to 32-bit with a modular framework. And then you can go to 64-bit with a modular framework. And it's the same framework at that point. The same equations will apply. So the only place really is here that the key optimization occurs. And it was just kind of an oversight, I guess, because again, if you're not focusing on performance, such oversights are possible. So we did some generalization to make it so that it could work for leading zero counters, not just of 8, 16, 32, 64, whatever, 128. We did it so it could work for any number of bits, because floating points are going to use like 32-bit floats will use like a 24-bit, or these kind of off sizes, long double size might use 68 bits. It's definitely worth generalizing it, not to just be completely within powers of 2. And then, yeah, so we did this adaptation, and I've got a lot of details about this. I think I'm going to kind of move along from most of the details. Basically, at the end of the day, we tried to get Max Compiler to do this. Okay, we tried to get it to infer this very custom specified circuit, but there's, as I said, the heuristics were messing things up. And at the end of the day, we had to make somewhat of a compromise. We tried to force things by making a lot of settings adjustments, and we got very close to actually getting it to respect what would be kind of like an intellectual property level solution without actually going that method of specifically defining every unit in a configure logic block with VHDL. So, and this here is representing to this intellectual property. This would be an IP level solution that we can't implement with Max Compiler. But if you use these formulas, you could implement something using those MUX F7, F8 units that would really fit perfectly in the configurable logic block. Okay, the example here, basically, a bunch of signals will be 1. These are all 0, and 0 causes these basic signals to be 1 if we look at the truth table from before. And basically, you can end up seeing in the end, you are going to get 14. I'm not going to go through the thing because it'll I'll have to go back a few slides and we'll have to look at all the tables. Obviously, the math for this, is not super easy to see because you have to look at a lot of circuit diagrams to see precisely how it's done here. But let's go to the results because that's what's important. We use Max Compiler 2021. Our FPGAs are Alveo U250s. This was our strategy. This was our synthesis strategy. We came up with kind of a framework for how you can try to do scientific measurements for something that's kind of going through this black box of Vivado and with Max Compiler sitting there. Although Max Compiler is a little bit more controllable, it's once you get to the VHDL, it's a bit harder to see what Vivado is going to do if you're using inferred VHDL. If you use explicit VHDL with instantiations, that's a different story, but that's what IP does. So also we tried comparing to other things like from Max Compiler, but the way that they would do it is using a leading one detect and then a one hot decoder. And that's why you can't use the default out of the box for Max Compiler because they don't really have this functionality. A leading one detect and a one hot decoder using an n squared VHDL algorithm. It just, okay, sure, Vivado will try to optimize it, but it's too inefficient. You won't be able to use a lot of floating point additions. So we validated everything. Some interesting facts of we used a Tcl script, we automated things with Python, we had builds automating searching for maximum frequencies using kind of a search algorithm, which took hours because it takes about 1 hour just to build anything with a real build. And
important results with this respect. I obviously will not go into detail in a few minutes. I just want to point out that this is an important point. I will use this thought of linearization from the 60s at the end of this talk, for instance. The main message here is that there are two typical approaches. One of them is that of pragmatic operations research dealing with semi-definite relaxations, cutting planes, etc. While physicists prefer to view it as an easing system, so that all the nice methods in physics which were developed for easing systems, including tensor networks, which I'm a great fan of, enter in the picture. And also we have some quantum hardware and not only quantum, but there are specific machines like the Toshiba Miller to solve such problems. Okay, so yeah, probably I have to click here. Yes. Now, if once you have such a thing like a cue ball, no, maybe I go back a little bit. Yeah, I skipped this slide somehow. So recall how it was with linear programming. When the solvers were available, then people started to model many things with linear programs. It was in the 60s. And essentially a whole scientific field grew out from linear programs. Obviously, if you're only tooling the hammer, then every program looks like a nail. Now the question is whether how good a hammer actually a cue ball is. So motivated by that, with my friends, we had the idea of attacking some kind of railway optimization problem. I had some background in railway optimization before, but I don't want to go into the detail of motivation. Everybody knows that if you're traveling on a train, you have a so-called train path, so you're going to time, and this is how the train where the train are located. Okay, so this is a timetable on which there are two intercity trains counter-propagating, and there will be a fast train a little bit later on. And these can be pretty nicely realized when these trains go, they stop at the station, then they proceed, and later on this time, what happens, actually I had this very experience, not the solution yet, I had this very experience in the morning today, but one of the trains is actually delayed. Now the minor problem is that if you don't pass the rest of the diagram, just shift the train because of the delay, and they don't feel. The sleeping will not be very nice, so to say, so they would actually collide. This is what we call conflict in railway operations. The solution is obviously that we have to find a feasible timetable so that no trains collide, whereas the difference in time from the originally planned timetable is minimal. Okay, so obviously passengers like myself, we prefer getting there around a similar time as it was originally planned, right? Now, for those who are familiar with scheduling theory, let me mention that actually this problem with the standard metaphor of scheduling theory, this is a blocking job shop problem. I skip this, we don't have too much of time. For those who are familiar with this kind of notation, now I told very exactly what problem I'm solving. For those who are not, actually it's worth taking a look at scheduling theory if you're in search of interesting part problems, because this is a very well categorized field with a lot of applications. Now, what we did was actually attacking this problem. We have Python, so this we kindly considered the minute revolution because we wanted to solve it on big day, and our variable, decision variable, it was a 0-1 program, essentially describe like how much of delay will each train have. Okay. Now I will not go into details, you can read it in this very contribution. Actually, the referees were not too much fond of this, but this reflects the general attitude of the operations research community towards quantum computing. I think said about it at some degree at some point. Anyway, it's actually an interesting thing. Nevertheless, we have results. These came from debate. Okay? The green ones show feasible solutions, but this timetables which were possible to realize. The red ones show non-feasible ones, and the reason of this mixing is in the choice of the penalty parameters, which in principle, in theory, they can be found exactly. Actually, that contribution didn't exist yet when we did it, so it was an educated guess. Nevertheless, it illustrates the challenge in finding proper penalty parameters. And here are some particular redesigned timetables coming actually from eBay. Actually, the problem was also affected tensor network methods, which I find a very important point because tensor network is a very neat technique, and once we have cuboids, I believe there is much power in this direction. That is hence in the title is physics motivated. The physicists have been putting a heck of a lot of effort into developing algorithms to find the ground state of various easing problems. Now, these physical approaches are largely unknown in the operations research community, and vice versa. The physicists usually do not know much about the semi-definite relaxation of an easing model. I mean, not a cubo, but this is easing model. So I believe that in the near future, there will be a kind of constructive interference in the methods leading to new interesting solution techniques. Okay, so these are the gross data of the problem instances in this paper. And let me go to, instead of listing these, to the lessons we learned from this first attempt at solving railway problems in the So the physical device, if you just use it as a quantum annular without any additional trick, unfortunately, this has two new bits. Well, we are in a noisy intermediate scale quantum devices era, so it's fine. This is what we have. However, it's a rather noisy device, so it's a heuristic. And in principle, this big difference between the publication year of the archive paper and the actual paper is mainly because the operations research community said that these are toy models. You didn't convince that this thing is useful at all, because there's so small problems that, okay, if you've been into quantum and you appreciate very much that you can submit a problem to an effective quantum hardware, believe me, if you've been dealing with that for 20 years, then this is a great feeling, but this feeling is not shared by an operations researcher who said that why don't you just submit it to CPLEX and they will not charge you an arm and a leg for running your optimization, right? So but we didn't give up. Now, this is just a minor comment that what we were facing in addition, that because of this noisy nature, it often happened that actually V-Wave didn't sample the ground state, if it cares, right? So how can you make sure that you found the optimum? Well, I wish we could, because if we could, then it would be a breakthrough in complexity theory, but to my best knowledge, it can't actually be done easily. Nonetheless, we had an idea that from a kind of statistical model of a physical annealer, maybe we can come up with some parameter which, with some probability, reflects that we have sampled now. So if somebody is interested, the citation is there. But next, we went to a bigger story. This is the surroundings of Katowice, the big metropolitan area, and we thought that with the hybrid solver, which is probably the best application of today's quantum hardware, how far we can get with the same problem now on a practically relevant big scale. I will not go into the details. It will be soon on archive, so it's a pretty fresh result. The model is a little bit different, but in the same spirit, but that's better modeling, and use the hybrid solver of T-Wave out of the box to solve it. And the message, and this is these are the main message here is that it worked on one hand, and the computational time was almost constant, which is normal by the design of this hybrid solver. This is what we expected, but this is a big pro in a dispatching situation, and you have to tell which can go. Okay, so the lesson was which we learned. There are a few things I failed to mention, but actually the QPU, the quantum unit, was during the calculation, so it had a bit of an impact on the result probably. So I would say that in a practical situation, it's at least a valid alternative. I wouldn't tell everybody that go ahead and do everything on eBay, but nevertheless, in a practical situation, it's at least a big competitive model. This is good. The con is that this is a black box, so now we are pretty much up to doing your own hybrid solver. And finally, what I promised about this fourth linearization, the idea that we don't know a heuristic thing. It might well be D-Wave, might well be some physics motivated heuristic, like I don't know, simulated bifurcation. You get a candidate of an optimum, but how can you ensure that it's an optimum? And we had an idea which actually didn't work out too well, but nonetheless it's a bit interesting. But this is a linear, mixed integer derived over Q-ball. These W's are continuous variables. It's known for quite a long time. And we have two ideas to use the heuristic solution as a starting point in this MIT when solved with CPLEX. It turned out that it doesn't help. The other idea was that let's try and solve the dual problem, because the MIT, you can do some kind of duality, albeit it's very, very expensive and there is no additional structure of the problem, which actually we're not having here. Nevertheless, it's possible to calculate the kind of duality gap, which we were hoping that it will close. Actually didn't. So after 2 weeks, it still didn't close, which means that it would be an interesting research direction to try and improve on this duality stuff, because that would be a very nice thing that we could improve this thing, and this we also did with parallel tempering results. And yeah, I forgot to mention this important message that the simulated bifurcation, which is a physics motivated algorithm, the implementation of my friend Bartek, which is not a very well tweaked one yet, and we didn't do too much effort yet. It was still competitive even with the hybrid. So physics-based heuristics can do a good job. And I think that I'm more or less on time, so hopefully. Thank you.
Thank you very much. One turn. It's shown that there's no guarantee that we found that optimum. So how important is that is that we find the optimal solution?
It depends. In the very situation where this very application, which I showed, it's not so important. Even classical solvers do not solve it to the optimum, but it's strongly time limited. You can't say that tomorrow I will tell which intercity will go next from this station, right? So that's an important point. Of course, in this case, we are happy with bona fide solutions, but there is a competition with the classical method. There are problems, on the other hand, where it's interesting, or not maybe these.
I would have one. So it's like, I mean, things are getting more and more critical as we improve the degrees of freedom, and it's including more trains and more stations.
Sure.
So at the level of now, so what is the largest size of network, or what is the frequency of trains you can have like this in existing hardware.
Okay, it's in a way hard to tell because most of the solutions which are in practice really are proprietary. There are a few papers there though where you can figure out and I would say that classical solutions can do slightly bigger networks than that of ours. So the situation is not so bad. Ours could be scaled further. So we believe that it would work, and we have artificial examples with bigger train frequencies. So essentially it could be put into practice, but I don't say that one of the traditional methods is not as good as that of ours. Okay, the bigger problem is that in railways it's very hard, and it's an international phenomenon. It's very hard to achieve that something is put into practice. And there are a few systems like that. Years ago, I saw this Swiss one developed by a German company. Actually, that time they said that they have some sub problems. I wish I knew their exact sub problems, but obviously they wouldn't tell. In which they would be very happy if they had at least some good heuristic, because it's they just make an educated guess. They don't have time for the calculation. So that's what.
Yeah, so thanks. It leads to the second question of mine that in this model, what is the uncertainty you put into the system? I mean, of course, trains never start at a certain time and never stop at a certain time. So there's always a little bit of uncertainty. So was this taken into account?
Well, on a minute scale, it can be planned.
It's a minute scale as well.
Yes. In fact, it's fashionable nowadays in this field to make more detailed so-called micro models, which take into account actual speed profiles. But this is mainly because of like energy saving or such a thing. We didn't address this because our examples came from the Silesian railways, which is a bit similar to NAV, if you wish. So you can imagine that 1 minute is a fine enough scale. The robustness otherwise can be inherited from the original plan. So just this is maybe a better answer, that you had an original feasible timetable where, well, maybe not mathematically, but it was planned to be robust by the experts. And we don't want to depart too much from that, which means that it should inherit the robustness of the originally planned timetable.
Okay. Any further remarks? I didn't see anything, so let's thank my guest again.
I'm just wondering, would this work in a like a three-dimensional system, like with airplanes or something like this, with air schedule, as opposed to a two? The train is more of a two-dimensional.
Well, I'm not too much into aviation, but actually there is an application of quantum annealing in aviation, and this is a gate assignment. Otherwise, aviation and railways share some common features, but in principle, these are very much different fields. Nevertheless, this gate assignment problem paper, I liked it, and it was quite convincing. So all people also in aviation, they are thinking about. So this is what I know.
Okay, thank you very much. So let's use my test again. The last speaker of the session, Attila Bortik.
Yeah.
So the talk will be iterative nth order nonlinear quantum dynamics.
And
Maybe F is all right.
Right, I'm waiting.
Okay, so my name is Botti Kapila. I'm a PhD student at the Petroshua University, and also I work here in the Research Institute. As you can see, I will talk about a very limited part of quantum computation called iterative nonlinear quantum protocols and their dynamical properties. So, in general, we can describe the time evolution of the closed quantum system in terms of linear map of the density matrix. But if we divide the system into subsystems and make a measurement in a part of the subsystem, we can create a nonlinear time evolution of the state of the unmeasured subsystem. So to understand the main idea behind the nonlinear quantum protocols, let's look at the example of a two-qubit quantum circuit, which create a nonlinear time evolution of the first qubit. So initially, we have two qubits in the same initial state. Then we simply apply a CNOT gate, which acts as an identity on the second qubit when the first qubit is in the zero basis state, and as a Pauli X operator on the second qubit called target qubit when the first qubit is in the one state. This operation creates an entangled state of the two qubits. Now comes the tricky part when we measure the second qubit, and based on the result of the measurement, we select certain elements. We can think about that as we select certain elements of the density matrix. It is called post-selection. In that way, we can create a time evolution of the first qubit, which can be described by a nonlinear map of the density matrix. Of course, the cost of the nonlinearity is that we have to use a second ancillary qubit. We can combine this nonlinear time evolution with any unitary time evolution. In our most current works, we usually investigate a family of protocols when we apply a Hadamard gate after each nonlinear steps. A second order quadratic nonlinearity. Previous slide. So by adding one ancillary qubit, we can create a quadratic time evolution. If we add more ancillary qubits in the same structure, so we apply CNOT gate on all of them, then measure all the qubits but the first one, and accept the results, the state of the first qubit only when we measure zeros on the other qubits, we can create an nth order nonlinearity, an nth order nonlinear time evolution of the state of the first qubit. And of course, we can combine with the Hadamard gate or any other unitary quantum logical gate. Just a technical detail that we usually use the block coordinates to parameterize the density matrix. Therefore, we can convert the nonlinear map of the density matrix to a system of equation for the block coordinate, which are three parameters the coordinates of the block vector. For the second order protocol, this is a second order system of equation. In the general case, for the nth order protocol, we get an nth order system of equation. So we can create a nonlinear a circuit which create a nonlinear time evolution. After that, we can apply this simple circuit in an iterative manner. So at the initially, we have a set of qubits in the same initial state. Then we form a group of 2 qubits and apply the same quantum circuit for all of them. And then, therefore, we can transform the state of the set of the qubits into a new, we can convert the set of the qubits into a new set. Of course, the number of qubits will decrease since we have to measure the half of them, but we can iterate this process to transform the state of the qubits in a nonlinear way. And if we use our, if you use the block coordinate parameterization, we can describe this time evolution by a system of different equations for the block coordinates. And we can simulate the time evolution by solving this difference equation and studying the characteristic of this system and the corresponding dynamical system. So let's go to the results. So one of our first findings was that there is an invariant set. So truly, there is 2 invariant sets, but the first one is an invariant plane inside the block sphere. It also contains mixed state. So the V equal plane is always invariant, which means that if we start from a state which located on this plane and iterate the time evolution equations, we always remain on this plane. And therefore, we can reduce the number of required variables to describe the time evolution. The other invariant set is the set of the qubit states. It's the surface of the block sphere, that means that our protocol cannot create mixed states from any pure initial state. So again, it's easy to see that if the length of the original block vector was equal to 1, the length of the block vector after any steps is still equal to 1. The existence of this invariant set made possible to use a different parameterization. And if we introduce that V complex number instead of the 2 real parameters, we can get back the Riemann parameterization of the quantum state of the qubit. And in that case, we can describe the time evolution as an iterative system of a complex rational function. After the invariant set, let's take a look at other invariant objects in the dynamics. For example, there are fixed points, which are points which remain the same under the iteration of the time evolution functions. The pure fixed points can be determined by solving this simple-looking polynomial equation, which is in general case it's hard to solve for arbitrary n, but for given values of n, we can manage to calculate the fixed point of the dynamic, and also we can decide if that fixed points are attractive or repelling based on the corresponding multiplier. So basically, a fixed point is attractive if the orbitals in the dynamics converge in the direction of that point. We can also determine the fixed point on the invariant plane, and we find one important fixed point which has a crucial role in our dynamic, and I will show a bit later. But there's always placed on the invariant plane. Okay, after the invariant elements of the dynamics, I think the most important question is what are the possible outcomes of the protocol, or what are the limit cycles of the dynamics. And in this case, we found that there is three possible results, three possible end cycles. And interestingly, the first one is the center of the block sphere, which is the maximally mixed state. The other two limit cycles are contains pure states. The 001 state, which is the zero basis state, and the 100 state, which is the plus Hadamard state. And the C2 cycle contains the one basis state and the minus state. And in fact, we can calculate that these limit cycles are not just attractive, but super attractive cycles, which for us means that we need only a few time steps to achieve the convergence, to reach the limit cycles. Knowing the possible outcomes of the protocol, the limit cycles, we can determine the structure of the dynamics corresponding to the convergence. So we can determine the convergence regions. For example, on the structure of the invariant plane looks like this picture. So we have three possibilities for an orbital starting from an arbitrary state. The red color shows the region from where the initial state always converge to the maximally mixed state. The other regions contains states which during the time evolution purifies to one of the attractive states on the surface of the block sphere. So it basically means that our protocol can purify a relatively large part of noisy initial states. And it's important to mention that on the border of the different convergence regions are located the previously mentioned repelling fixed point. Then it's a bit C2. Then if we are looking at the convergence structure on the surface of the block sphere into the invariant plane, we found a more complicated structure. So the border of these different convergent regions, the pure convergent regions, which are the basin of attraction of the pure states, we find a fractal. From the theory of complex functions, we know that this is the Julia set, which is a fractal, and it is self-similar. And it has a fractal dimension equal to 1.5. Looking at lower purity surfaces in the block sphere, we find that the border of the pure attraction regions have very similar properties to the Julia set. Therefore, we introduced the term of the quasi-Julia set, which are the set of all mixed states, all mixed points situated at the boundary of the pure attraction regions. And this similarity between the Julia set and the section of the quasi-Julia set also can be quantified by estimating the box counting dimension, truly the fractal dimension of the border. And we find that the dimension is always the same, is a constant value above a critical purity. So if we are looking at the pictures on the left, we saw that for the pure attraction regions, the border is a fractal in the Julia set. And as we decrease the purity of the initial state, states that converge to the maximally mixed state occurs, but the fractal is still present. As we further decrease the purity, the fractal becomes less visible, but if we zoom into the small details where the two pure attraction regions are connected, we can still find the fractal. But below the critical purity, the two attraction region have no common border. Therefore, one can conclude that the fractal disappears when the two pure attraction regions separates from each other. So, therefore, we can redefine the critical purity as the purity where the two attraction regions separates. We calculated the same phase transition like I forgot to mention the most important thing that the process looks like a first order phase transition, and we can identify this phase transition for higher order of non-linearity. And interestingly, we find that the Vox-Hampton dimension of the Julia set is the same for any value of n, but the value of the critical purity increase as the value of n increase. And it can be explained by that the critical purity is equal to the purity of the internal repelling point. And we numerically calculated that critical purity of the dynamics and the purity of the fixed point located on the border of the three different region of attraction. And we find that the two value is equal. Therefore, we numerically prove that our statement. And this brings me at the end of my presentation. Thank you.
Full time for questions. Okay, so I think since the time is very much used, so we can quickly move on. Thank you for the diagram. As I told you, can do nothing, but we are comfortable with the next scope for asking that with the next presentation. We will be on FPGA development and we want to design.
Azt csak beállítom a képet, mert te látod, itt körben megvan az zöld, meg eltűnik, úgyhogy gyorsan beállítom a képernyőt, hogy normális legyen, aztán folytatjuk. Most nem látom, basszus. Hát meg vagy. Ezzel van benne pointer is. Itt a srác. Van a súlyogépen, mint az atom. Nem azt próbálom, most éppen azt próbálom, hogy a gép is miért kivetítőnek, mert látjátok, le van vágva a kép. Amit lehet, és az még majd jön utána, most az elmúlt. Jó. Nem tudom, mi van megnyitva, de van úgy lassítja a gépemet, mint a atom. Jó. Említem ide. Tökéletesség igénye nélkül. Melyik van bizony? Igen. Nem, a gépen van már belassulva, nem tudom, hogy mi volt a előző előadásban. Én nagyon nagy felbontású képeket vetített, ott már látni, most már kiakasztja szegény. Még azzal, hogy még HD-ban nyomja ki a képet is magából. Jó. Megy. Meglepettem, hogy a többit is, amit nem tudtam járni. Most mondjátok, mert itt van a következő előadásnak a ideája. Mostan az ilyen. Vannak még ezt nem elmondom, csináljuk azt, hogy kitöltsétek. Az is fut ki, akkor gyorsan. Egyel vissza. Momenta. Mert még felismeri. Lőnöm a... Nem, próbálok itt nyújtani a terheken. Na. Jó, tölti, jó van, remélem. Össze ki megint ne fáradni. Igen, most itt is lesz. Mondom, hogy tarthatnánk egy kis szünetet, és addig rátöltjük a dolgokat, nem mit tudom én. Jó, csak az elég szünetet, nem úgy próbáltam. Azt értem én. Mi van benne? 7 éveset ne vegyél. Most ja. Most már mindegy, most már hagyjuk lefutni. Most már ennek kezdjük előről, nem most már le fog egy pillanat tölteni, csak
Nem tudom. Ez nem jó.
utána aggódsz. Hát akkor majd megkeressük benne, bocsánat. Megkezdődik, és remélem ennek a své. Safe for work. Not safe for work, az a NFS, a NFS a Windows-os system. Oké,
Most megvan mind a három? Vagy
jó megyünk. Az előadás mappan teljesen.
az egész alapban egy videó is van.
Jó. Jó. Ez gyors volt. Ez túl gyors volt. Úgy látom, mindennek van file mérete is, tehát akkor lecettelni mindent. Jó, akkor másnál itt csak, de akkor csak menjen a buli tovább.
Jó, most minden talk le van, tehát nem fogunk időt veszíteni.
De ez jó. Hogyha most minden nem van, akkor tudod, hogy hogyan kell. Azon belül. Ezt is el lehet venni.
Okay, so we are flying forward. So the next speaker is Andrew David, and as I said, the talk is about implementing self-GBT and LPGBT link arrays in inter-area and FPGA. So this is again FPGA related talk to present. Hi, everybody. I have diver in the Wigner data acquisition laboratories and in the data acquisition laboratory, one of our main fields is to participate in the CERN ALICE experiment, data acquisition and further and further development. And today I want to talk about the CERN development, GBT and LPGBT protocol implementation in a custom inter-area frame-based FPGA card. The reason for this is that the GBT protocol is the older one that's already implemented and already used in this run, but now we are started to working on the LPGBT upgrade, and that's the reason why it's on the table now. A little background that in the last project, we have the main experiment around the circle, and it's below the surface at least 100 meters, and the so-called counting room is on the surface. So from the beginning, there needs to be connection from the counting room to the detector area, the so-called downlink, which to do the measurement, we have to distribute the LHC clock, which controls everything in the LHC experiment, in the measurement, the trigger information and some flow control, like reading out the temperature or starting the measurement. The uplink, the way how the detector send out the data, even counting in in previous round 1 and 2, this downlink and uplink was implemented with different cables, like the TCP link. The trigger link was optical cable down to the camera. The flow control was through the Ethernet to TCP/IP protocol, and the video link, the uplink, the detector data to the server computer to the data taking FPGA was the so-called DDR link, which actually was developed by the Wigner acquisition group. For round 3, they replaced the links with the so-called GBT links. One of the achievements of this link is that you don't need separated cables. You can use single optical cable to transmit down the clock and trigger information, flow control, and you can get the data. And for round 3, for the new detectors like the planned focal sub-detector, they plan to use the GBT link. The LP GBT means gigabit transfer links. LPGBT means low power GBT links. Okay.
The difference between the two sides of the data export side in a high resolution area, it means that the typical is like static language that can be started to the internet after, but one due to the high radiation, particles can hit the big things like that and get grow the functionality. That's why it's CERN that the electron beam will factory which design such way that can work properly in this high radiation zone. This is actually, and they also design the so-called red styling, which is a optical transfer which also works in the high radiation zone. On the surface, we can use any commercial available FPGA, like usually they use the Dynamic or the Arterex, now the interactive build. And basically, this side is a VHDL source code, which is the timing and implementation, the data acquisition information, the flow control, text everything into the local GDP or FPGA packages, and it will send down to the ASIC, and ASIC will extract all the information and do the communication. With commercial the desktop you can implement Fusion, but in actual experiment you need estimating as you can get. So this is a custom card based on Intel Area FPGA, which can handle up to 48 digital LPDB. This is a short summary about the latest LPDB features. You can see that it receives the data stream from the data tagging FPGA, and it extracts with the different readout cards along the data source. It provides fixed and deterministic latency for clock and data distribution. The downlink is 2.56 gigabits per second. It contains a forward error correction. It has only a single speed. The uplink can be 5 or 10 gigabits per second with two different forward error correction scheme. This error correction is for even if there is some bit trips due to the radiation, then you can find and correct some of them if it's below some level. This new ASIC also contains some built-in devices for controlling and monitoring, like converting analog to data to digital or digital to analog, built-in temperature sensors or I2C masters, and some GPIO pins to control the content card. This is a short summary. The 40 megahertz is the so-called LHC clock. This means that everything happens at the 40 megahertz. So if we want to send down a package, then we can decide how many bits we want to send down. In this case, we send 120 bits per clock cycle. That means that 4.8 gigabit per second will be the link speed. The package is constructed from a header part, which is always a specific bit pattern in the data stream, and we have a different
fields, internal control, external control, user data, forwarder code, but this part is scrambled and interlaced. It's, if you just look at the line, you can see the header in clear format, but everything is just a garbage because randomized due to the DC balance. This is same for the uplink. So if you want to communicate with this ASIC, you have to send packages in these required formats. Okay, a few words about this card, the custom FPG card. It was developed by LHCb Experiment, and that is opted to use the same hardware to because developing such a card is a quite complicated task. It's like a GPU card. It has a 16-lane PCIe Gen 3 interface toward the motherboard. It can accept up to 48 GB or LPGPT links. We are fortunate because this FPGA, this Intel Arria 10 GX, contains 96 built-in transceiver, which can work up to 12.5 gigabit per second. So our need 2, 4, 5, 10 gigabit per second is covered by this FPGA. This is fortunate. Happening. This card contains 2 SFP plus connector to communicate with the trigger system. Okay. This is a high-level block diagram of how this can be implemented. This is still a, let's say, single link. The GPT-LPT architecture was developed by 7 electronic groups, so you can buy the ASICs and optical part, hardware. But to use it in your data acquisition, you need some FPGA code, and this blue part is provided by the 7 electronic groups. You can access this publicly. I provide the link if you are interested. But to actually use for your physical experiment or your measurement, you need to provide some FPGA specific solution, transceivers, PLLs, and so on. And you have also do some detector specific coding. How, because basically in user specific logic, you issue some command to the GPT downlink, which will receive the GPT or LPGPT ASIC, and this will be converted back and will be handed to your specific ASIC on the front-end card, because typically in this higher radiation zone you cannot use another FPG, but also you need a radiation hard ASIC like SunPower, Alpine, a pixel detector or something like that. This is the typical use case. And you can send back your data, and if everything goes well, this green box will receive the data collected by your sensors, and after some formatting, you can pass to the DM engine, which will transfer the raw data to the server computer in the company. This slide is about how we can distribute the clock, because it's very important that it must be in deterministic, fixed and deterministic frequency. It's actually maybe it's very, but it's very simple. this is the elastic with the 40 megahertz, and at every rising edge, we have a dedicated header character. This in this protocol, this comma key, which we can transmit by this trigger unit. So it's a periodical thing. Between two header, we have the actual payload, and what we have to guarantee that we can deliver the LSD clock to every front-end card. We just need to keep our part in to do our part in deterministic way. And if everybody do this in deterministic way, then the result will be also deterministic. So basically, in our FPGA, we just catch the header characters, we reconstruct the clock, and according to this reference clock, we send out the GBIT and LPG packages with header information. And if this reach the ASIC, the ASIC will be able to reconstruct the 40 megahertz, and this difference will be a deterministic time delay. And very important that this must be same delay between the power on cycles. That if you tomorrow switch on this device again, then you get back the same difference, and also between the FPGA firmware recompilations. That if you recompile your firmware, you get back the same delay. How we can send the GBT package from the FPGA? Usually we think that in the FPGA, because it's a pure programming data, it's full with flip-flops and lookup tables, as we heard before. But for sending out serial data at that high speed, we need a dedicated transmitter and a dedicated receiver. And this yeah. So in our Ariadne FPGA, we have such a transmitter and receiver pairs, local transceiver around the edges of FPGA, and we have 8 to 6 of them. But usually you cannot use just one of them independently. The hardware is optimized or work in such way that it's organized in group of 6, the so-called transfer bank. So if let's say if you want to create a 48 GBT lane, then we have to utilize 8 of this transfer bank. Usually, we can select the peer type property, then distribute them to the transfer to the internal clock distribution line, and provide the parallel data pairing and accept the parallel data pairing. This slide tries to explain the whole system in more detailed way. Basically, we have externally the trigger, central trigger processor and the local trigger unit, which send us the clock and trigger information to the FSC transfer. This is also 10G1. Then the reference block is extracted from this ring, which is 6 times 40 MHz, 240 MHz. And this block is provided to the user logic with the trigger information, and also this block is sent out to the external digital signal, which helps to get better clock distribution results. And this reference block is feeded back to the ATX PLL, which we have one PLL per transmitter bank, and we can have actually 8 transmitter banks. This is the transmitter part, the so-called downlink part. We can turn down the command to the content of the starting the measurement, and through the receiver part, which is the uplink part, we receive the DBT data stream, and we can pass the user logic, and this user logic is packetizing the data and can pass to the DNA engine. This is just to look into that, how it looks in the reality. This design is rooted design. This structure forces a digitally, and you can see that how this represents a single transceiver bank. It's a PL, and you can see that they arrange around the edge of the FPGA. And what is interesting that you can see that this is the use a fabric logic inside the FPGA, and this happens because we have to when we receive the incoming stream, each optical link can be different in length. So we have to maintain one program per digital link, and this is how the area can manage to keep the timing, but there is a so-called peripheral distributing resources, which exposes the face to the close to the surface. And this one is a more realistic use case. Typically, they use the 24 links because this is on the FPGA in this there is a shown the effects the research which shows even if there is usually different parts of the kernel. I collected a few links about this project which you can access freely. Only the LHCR return is requires membership, but all other information is available for you if you are interested in more details. Okay, thank you.
Thank you very much. And for the control for
So we synchronization, I think you have to want to find different events. Send data, you know, I think, synchronized.
Yes, it's a very good question. On this side, okay, for receiving the information from different visits with random phase difference is not an issue because the critical part is when you take the measurement that you have a nanosecond precise timestamp on the measurement. After we receive, there is some processing in the same clock domain, but after we have a FIFO to put them in a common clock domain. The critical part is the trigger distribution, and there is a mechanism that from this clock domain stems from the 160-bit trigger information, and it must be ensure that each DVT transmitter logic reaches with the correct finding the setup and hold time requirement is fulfilled. This is kind of in the kernel of the framework. It's an issue, but it's managed to solve it.
Okay. And one or why resource in one. Looking for the next year, we have policy and it's about application on because simulation framework for very active.
Az nem igazolna a mikrofonokról a hang, tehát hogy értek, hogy most legyen hang, vagy nem legyen. A ventilátort azt nem tudjuk lekapcsolni, mert különben meggyullad a gépen, de arra gondolsz.
Nem azt, hogy a hang a laptopnak ez nem adja ki.
Ja, az le van véve.
Az a hátérnénken ezt az megy a hang, úgyhogy rajtam előre. I hope everyone hear me correctly. My name is Margot Mark, and I'm a master student in the University of Technology and Economics. I'm I am an active member in a Guardian Code Development Team in the Institute of Nuclear Technology in the Heidelberg University of Technology. And I participate in the work of testing and implementation of various Monte Carlo variant reduction techniques. Application in Monte Carlo code and especially in Guardian, which I'm going to present you. In the field of reactor physics, the Monte Carlo code, especially the dynamic Monte Carlo code, are very new technology and very promising because they can provide a very accurate calculations and due to they are becoming an essential part of the safety analysis, which is the main purpose, one of the main purposes in the field of reactor physics. And the Monte Carlo, I hope some of you familiar with Monte Carlo technique. The Monte Carlo algorithm purpose is to estimate integral equations, and in the field of reactor physics, the dynamic Monte Carlo code solve the integral form of the Boltzmann equation. We can choose two main algorithms to perform Monte Carlo. One of which are Monte Carlo. Monte Carlo code purpose to estimate the in a field of particle transport to estimate the response in a detector, the certain of interest in an area of interest in a phase space. And we can calculate that some contributions of the particle histories during the time evolution. And another case, there are real physical phenomena. The neutrons are represent real physical entities, and the variance of the given phase region we are interested for is only function of the population of these particles. So our goal in this Monte Carlo simulation to simulate as much particle as we can, but also this population governs the computational time. Because, in theory, we can get the exact solution in every situation if we can simulate all the particles and with all the trajectories. But in reality, it is not actually possible because we will need enormous computational power. But there are techniques that we can make efficiently these calculations with introducing of Monte Carlo techniques with variance reduction. In this case, Monte Carlo doesn't follow the real physics phenomena. We assign the particle weights and in a part of the simulation. Used to compensate the distortion of their probability density function, which we are sampling during the simulations. These events can be particle three-patch sampling, or the transition, and any reaction or like fission or absorption which are taking place in a reactor. There are several variance reduction techniques, which main purpose to control the population, getting us constant value, and also take some computational time and made with the variance. That's the name. I would like to introduce the Guardian, which is direct time dependent dynamic Monte Carlo code, developing into the nuclear technology, and Budapest University of Technology. The Guardian simulated direct and time dependence of the neutrons, and is written for Linux environment in C++ and Java, and runs in GPU code. You can capable of answering with energy handling, means there are energy grids for the reaction, because every reaction depends on the incident energy and the angle of the incident particles, and has temperature and also atomic number dependency. These cross sections are stored in a huge nuclear science library, and the Guardian interpolating in between the specific values in the region. The Guardian contains several variant reduction techniques with a finance and to control the population. It's very important because the Monte Carlo has excellent parallel computation capabilities, but there are strict conditions for that, because the first of all, for the mentioned, we can take this parallelization because the particles history, the random bond of the particles doesn't contribute to each other, and from every CPU core can compute its own set of particles, and you can exploit this parallelization, and even more if you use CPU logic set. But there are strict rules for that, because we can use this technique if the population and the weight not varying very much during the calculation, because the multiplying system doesn't accept isn't acceptable for the specific algorithm. Due to because then for example, execution is taken place, it would be in our case the neutron is multiplying, so there will be more neutrons. But in the case of non-analog case, non-analog game, we just increase their weight, and we cannot handling in a computation of the utility stack. The precision is very important in the dynamic code, especially in the geometry and in the positions of the isotopes and the neutron. So the Guardian is double precision arithmetic, and very important for the thermal hydrolysis coupling, because the reactors are complex systems, and the neutron transport depends only on a thermal hydrolysis feedback, and it is very important for the reactor stability and it's for safety. So
In general, we suppose couple with thermohydraulic coupling, with thermohydraulic force. The gradient has been coupled with the suction flow thermohydraulic force, the second is force. The suction will make flow area which is delineated from the adjacent fuel rod in a fuel assembly. In a nuclear power plant site reactor, there are hundreds of fuel assembly and the hundreds of rods in a fuel assembly. So these are very big geometry. The suction flow for the basic conservation equations like NH momentum and mass and for the conservation equation is finite volume method to axial and radial direction and contains empirical correlation. The coupling scheme is a much more interesting part of the whole coupling. How we implement the control code, how to connect, how can we connect that to the redundancy code, and one method can be the implicit operator switching method. In this case, the first of all, we determine the power distribution node-wise and node-wise power distribution in the beginning of the time step. And these values goes to the thermohydraulic load, get the power distribution and calculate the temperature and density data and gives back to the electronics to calculate the next time step. And the dynamic coupling scheme can be separated three phases. The first phase is first conversion. When we start the simulation with first conversion, and we show the names, part purposes to reach the convergence of the code. First, the guardian needs the initial power distribution, and the suction flow being the static mode. You don't use the desired temperatures and densities. These are important to the thermohydraulic feedback because the first fraction of the reaction, as I mentioned, temperature and density dependent. In general, in the Guardian, one coupling time step is approximately 5 milliseconds, which means that the Guardian has a time that's 5 milliseconds, but the Johnson time step is much shorter, in order to 10 to the minus 5, 10 to the power minus 5 seconds. And the substance flow one time step is the coupling time step, which is 5 milliseconds. But in the static case, there is no time limit. It continues until it reaches the convergence. And there are the one convergence step, one cycle is called inactive cycle, and goes until it reaches the convergence of the coupling. After that, we generate the factor of the and the thermohydraulic is on call.
diagnostically model example, then the effect result means the activated isotope. I will see that result. It's not really interesting. The more interesting part is the simulation results. One of these functions is a benchmark from the Prima Island Darkstone model. The 40 centimeter control moving function. The function time was 5 seconds, and we simulated 4.6 million nanoton. The result. So we can show the time evolution of the power release, which is, and this thing rate, which are continuous for normal, the time is couple time 5 milliseconds, and the continuous is 100 milliseconds. And want to show some comparison other dynamic simulation quantified simulation. These are the tripoli and the right? Tripoli and the pattern. These are validated and the public codes in a with the science, and with the same parameter set, we get the same results from the same coupling. But some cases, the power release was overestimated. So it can be seen how important the coupling time step, the higher the coupling time. Before the function is not moving, then we wrote the upper cover. With a much smaller time step, we cannot get high power release. Due to the much faster thermal impact. I want to show you the comparison of the fuel temperatures. When we also we see the same, almost the same results as the competitions. The difference is the order of the Kelvin. So the guardian with the subject to start from the fine color. You actually with 90 and actually 6,000 shots. And also want to do some computational time. There's continuous neural moving space with the active 300 shots. With a simulation to 462 hours. For 188 hours, and we can see the thermal physical disorder make up the 2% of the competition time in the whole simulation. And also and also want to show you a video from the simulation. 5-second transient. Okay.
Yes, it's better. Lento. Ecco. More spectacular picture of it. Let's go. You can see above the temperature distribution and below the power distribution during the road moving sound and maybe my codec maybe not so good right now. Long time not used the VLC. Sorry. Sometimes it's like since I don't have enough time to situation, but thank you for your attention.
Couple of time that maybe I personally we have in the second.
Yeah, of course. The second generation wanted to be steady state simulation for a MPP. These are the results from the cross section of the core, and there's the power distribution, and these are the given temperature, and that's for the steady state calculation, and it took 90 hours. All right.
Any remark or question at this point? Not less in smart event. Next speaker is on Powerpoint, and going to speak about this time this in AI. And this is analysis.
So Weichmann rates hourglass. Bocsa mój.
So this will be an artificial intelligence talk, so it's a little bit different than the previous ones. And system 1, system 2 will be explained later. So let's start.
How I did both better.
So everybody, I think, here is aware of the recent impressive developments in AI. It's the revolution of generation, AI generation. Yes, this is anyhow. So there is a big revolution in text generation. So we have the ChatGPT as a new tool. Probably everybody has tried it. If not, then it's very much very useful thing. And there are descendants of that, like OpenGPT. There is the AI, Bard AI, the Microsoft, and the Google variant of that, and so on. Image generation as well. Great tools are there. So all of the pictures here are generated by some image generation tool. Midjourney. This person doesn't exist. This tool right under right corner. These are generated faces. That leads to the Gen5. So it's a big revolution, and it's not so this big revolution has led some people to think that maybe there is some doomsday, AI doomsday nearby, that the AI will be so developed, so smart, then they will do mass. Now, but on the other hand, when one actually uses these tools, may have the impression that although they're intelligent and useful tools, they're very heuristic and sometimes very stupid. So if you generate an image, for example, a guy who does his lace and his shoes, and it turns out that the guy has 3 legs. And the image generator doesn't realize that this is a problem. It presents you as a solution. So sometimes, and also some people say that the ChatGPT is lying. But if it actually doesn't lie, he doesn't know what is the truth. It's trying to generate some text. So the question is that why do they work so well sometimes, and why do they fail so stupidly sometimes? And this is the question I want to answer in this talk, not in the full complexity, but some hints about that, some thoughts about that. So first thing which we have to be aware that the human intelligence is not a monolithic entity. This is the Cattell-Von-Terror theory showing the parts of the human intelligence. It is divided according to different sources, 8 to 10 parts containing the fluid intelligence, which is responsible for vision and analysis, crystallized intelligence, which use acquired knowledge, and so on and so forth. A lot of parts of the human intelligence is there, and part of it is visual or auditory perception. So this is far from being a monolithic entity. And another way of categorizing the human thinking, of human intelligence, is the modes of human thinking by Daniel Kahneman. And he divided the human thinking in 2 parts, the system 1 and system 2 parts. The system 1 is a fast, automatic, and instinctive thinking without conscious awareness. That's the way how we function when we drive, for example, without listening, but we do actually we switch gear without knowing that we do it, or we do this. We have learned ride a bicycle, then we don't have to take care about what we do, or just or a musician who plays well with his instrument uses system 1 system. This is fast automatic, but this system is more prone to biases and errors due to the heuristics it uses, and it is very appropriate for giving fast responses. And system 2 is in some sense just the contrary of that. It's much slower, but it is conscious. When we speak about intelligence, or a guide is intelligent, we think about the system 2 system. So we refer to the system 2 system. So it's deliberate mode and controlled and accurate, but it is more slower.
So if we learn to how to drive, for example, then we have to listen all of the details. How do we hold our hands and what happens in the neighborhood? And after a lot of training, we can switch to system 2 to system 1. And this is then everything goes much faster, but it is much more error prone. This other thing. So what is the corresponding things? What are the corresponding things in artificial intelligence? Are there corresponding categorization in artificial intelligence? That's what I would like to speak about. So, okay. So in human thinking, when we speak of the human, there are no extreme unbalances. So everybody uses all parts of intelligence. It's not that somebody just can talk and cannot see anything. Or have no visual memory or have no memory at all. It doesn't happen. There can be some unbalances, but not extreme unbalances. And we use both system 1 and system 2 parts of our thinking. Unlike in AI models. In AI models, they just focus on one part of the intelligence, one part of the mode of operation. And that's why that when we look at a splendid tool like ChatGPT, we tend to think that it has a general intelligence and it can overwhelm us in every part of the life. But it is not true, because in AI models, the intelligence is very unbalanced. And actually, the performance of AI depends very much on the task we want to solve with it. And there are 3 different tasks that is popular in the artificial intelligence. The first is nowadays is not so popular. It was the first task that was given to the machines, that is Turing's task, that by the definition of intelligence by Turing, it means that intelligence is a system with which we speak, we talk, then we cannot decide whether it is a machine or a human. That means that it is intelligent if it talks like a man. But it leads to tools which try to deceive the observer, to cheat the observer, to think that it's much more a psychological game than an intelligence system. Now, the second thing is the classification task, and it will turn out that it corresponds to system 1, and the data representation task, or representation learning, corresponds to system 2. So in artificial intelligence, there are corresponding systems, and that's where I sent now. What is the classification task? So then the intelligence is defined that a system is intelligent if it does the classification like humans do. For example, we can make a distinction between dog breeds, and if a system can make the same distinction between the dogs, can separate in the same way, then it is an intelligent star. There is some mathematical background of that, so it's a very well built-up system. This based on Bayesian analysis, when we shall assess the probability of belonging, an item belongs to a given class. Typically, this use the loss function, global parameter fitting backpropagation. This is the AI which is usually used now. This is the structure. And the paradigm which it uses is the supervised learning, as the task suggests that it should categorize like us, then we have to train it to categorize like us. So we have to annotate the images, for example, or the text to train the system how we do the classification task. So as I've said, the most successful present-day AI primarily work in this way. So we have the classifiers. For example, this is the Cypher database, which has some categories, and all of the images should be classified in some of the categories. But there are very nice classifier, for example, bird songs or faces on dog breeds on mobile phones. So it's really splendid and very, very nice. These are the large natural language processing models, the large language models, which we know. This is also based on a classification task. It tries to assess the next word in the sentence. So, and it can be used for recognition and generation as well. And the technology, it uses primarily the deep neural networks, image recognition. For image recognition, these are the most used ones. For language models, these are nowadays they use the transformers, and some variants which very marginally can be sorted in this way are the general adversarial networks or the variational autoencoders. So this is the classification task which led the people to construct the present day AIs mainly. But what are the properties of this classification task and these models? They are very fast, very effective, very good interpolation properties, but there are some disadvantages. For example, the training is very slow, so it can take weeks or even months on supercomputers, and they need a lot of data where they use a larger amount of parameters. For example, the ChatGPT uses 500 billion parameters, is a very large amount of parameters, and very important that it has no control over the mistakes, as I've said earlier. So, for example, and it is therefore it is prone to adversarial attacks. For example, here this image and this image for us is the same, but there is a very little difference between the two. This is just some noise, but still this is recognized as a panda correctly with 58% of confidence level. But this is recognized as a gibbon, if you can't read, with 99% of confidence level. So this means that something there is no control over the errors, over the mistakes. Yeah, it's a delicate thing. I will skip it. And very interestingly, and another disadvantage is that it's very specific. It's designed for a given task. So if we design a system, a neural network for a given task, and we want to switch a little bit to the task, then we have to start the training again, not from the very beginning, but practically we have to repeat the whole training task. This is called catastrophic forgetting. And as you see, all of these properties, advantages and disadvantages, correspond to system one thinking, which I've mentioned in the introduction. So actually, nowadays, the present day AI are system one systems. These are not really intelligence in the human way. They give the response in an intuitive, gut feeling way. So these are just guess, the correct answer, but very educated guess, we shall say. But what are the system tools? Are there corresponding methods for system two? And if we consider the task of data representation, which is the sub area of representation learning, then we can do this leads to different thoughts. First of all, these are data-driven methods. That means that we have to present, we don't have to annotate the data, we have to present the data which we think that they share a common property. Okay, context dependency is not so important, but what is the method? What is the method we shall follow when we want to find the best representation of the data? Actually, we have to separate those properties which are important to represent the data and which are not important. For example, if we do a physical experiment like measuring the time period of time for a pendulum, the position of the Mars, for example, is an irrelevant thing. Anywhere the Mars is, the pendulum has the same, more or less, actually, the same period. So that means that there are irrelevant features, which doesn't change the measurement results, doesn't change the class actually of the classification task. And there are relevant, the opposite ones are the relevant features. If we change something, for example, we change the mass of the pendulum, then it will change the period. These are the relevant relevant parts. We can say this, the following. We can think the following way, that if we change a relevant thing, then it changes the class. This is this can be used as a definition of the relevant property. And that also follows that relevant property is constant over a class. So this is the main idea behind the representation learning. So we have to find those, once again, we have to find those properties which are constant over a class. That means that we have to find the laws of the class. These are the constant properties. For example, a Newton equation is true for any mechanical motions. So this is a law, this is a relevant property. Okay. So this is, I don't know how the time is limited, but I hope that the message came through that this is to find the best representation of the data, we have to concentrate on the properties which are constant over the classes. And we can manifest it technically as a feature transformation, a law-based feature transformation, that we separate the relevant and the irrelevant features. And we can also characterize the effectiveness of the realization by an entropy, which we have some reference. We have wrote some papers about that. Okay, what are the advantages and disadvantages of this method? The advantages are that we have we can have several laws. For example, we have a Newtonian law, we have conservation laws, and so on and so forth. Or for a cat, if we see a cat, then there are laws. It has 4 legs. It is furry. It has it has 2 ears and a cat-like face and things like that. A cat-like shape, which cannot be quantify very much, or at least I can't quantify now, but we know in our head these are the laws, and if anything doesn't match, then we don't say it is a cat. We can think that for example, a cloud resembles a cat because some properties, some laws are sharing, but we don't think that there is a cat on the cloud because some other laws doesn't fit. So this is why this system, good realized data, good represented data are very much stable against mistakes. Okay, it is a technical thing. It can be used with unbalanced data. There is no forgetting as opposed to the system one systems or the DNNs, for example, because we can collect the laws which is characteristics for cats, and we don't care that we want to categorize also dogs because the laws of the cats remain the same. And if we collected all of them, we can realize the cat at any circumstances. And it has a much faster training than the system one DNNs, for example. But this can have disadvantages. The first disadvantage is, of course, that it can be, if we have a lot of laws, that it can be slow. It can be much slower than the DNN, the deep neural networks. Okay, but anyhow, I think this is a good way to proceed to go on and try to find try to solve the same artificial intelligence task than has been solved with DNNs. So let's try to do it with this new method, this law-based transformation method. And indeed, we have some applications now, and then I'll show up some of our results. The first one is the ECG analysis So the goal is to classify heartbeats into normal and not normal, which is called ectopic beats in this area. The input are the ECG signals after cleaning and standardizing. The method we have followed that, okay, of course, we have prepared the test, the validation, and the training set, and found the linear lows for the QRS complex, which is shown here. So this is the middle part of the heartbeat, the QRS complex. And these are for normal or healthy beats, these are for ectopic beats. These two should be separated. And the method is that we split this into small parts and try to find out what is the low of the normal, of the healthy QRS complex, and what is the low of the not normal ectopic beats. So we collected lows, which is constant over this data set. And the results are very well, good, at least up to the state of art. This is about 95%. And we can actually improve this accuracy. We have more data sets. Okay, and then the second application is an activity recognition system based on multi-sensor data fusion. It's a database, a publicly available database, which where it is recognized the motion of humans. They have stuck 3 markers on the body and recorded the time evolution of these markers as the person did some movements, for example, bending, lying, cycling, and so on and so forth. And the task was to knowing the signals of the 3 markers, that we have to tell what is the motion that the human did. And in this case, apart from technical data, we have managed to achieve an error-free, errorless determination for 100% categorization, error-free classification, which is of course the best in the world. It cannot be improved anymore. Actually, the DNNs provided 97%. So it's the world's best result actually in this area. It's a particular area. Okay, that's next. There is a physical application where we have feeded the emotion of a mechanical system, and the system determined the Newton equations and the conservation laws, so determined the laws automatically and continued the motion. This was the project we have, and it worked for integrable systems as well, like pendulum, also with chaotic systems like the double pendulum here. And it gave a stable and a stable solution which fits with the exact solution if the fitting is possible. And this is again, of course, based on laws. We also have studied stochastic processes. In this case, the laws tells that assuming that a system is a Markovian, that we can ask that how many degrees of freedom are there. And with this method, we did this law could tell us the number of degrees of freedom. And it's very interesting. Here you can see this is the Bitcoin price movement, and this is the dimensionality of the motion. Actually, the largeness or the value of the third dimension. How important is the third dimension? I mean, not a two-state or three-state Markovian process. And we see that usually this is a two-dimensional. The laws changed in these regions. It's after COVID region, so we don't know why. It's just no observation. So it could be. So it is worth to speculate about that. So that anyhow the data analysis shown which was not known before. So it's a new result actually that something have changed in the Bitcoin prices after the COVID for 2 years, and that after it is again ceased to go on. So this is my conclusions. So as I've said, artificial intelligence is not a general intelligence. It's very, very much constrained by the task we give them. If we give the Turing's intelligence that definition, then we get programs that deceive humans to think that they speak with an intelligent actor. If we give a classification task, then we get the system 1. And if we give the representation task, then we have the system 2. And I think as we humans use both system 1 and system 2, a possible way to go on to mix these two approaches and build a system 1, and above the system 1 or from system 1 parts, we can build a structure system 2 system. Maybe this is the way how can we improve the present day artificial intelligence tools. Thank you very much for your attention.
It was very, very exciting talk, so we have time for questions.
Two questions. The first one, this is the first one is going to be just a silver. So you mentioned in projects where you want to figure out what the emotions of people are doing. Because you were using a way of using 3 sizes.
Yes.
We have 4 these. So
Yeah, that's right. So probably some motions could be resolved by this method, but I think this was attached to the arms and on the leg. So probably these are symmetric motions. So if the person would move just one leg, which was not marked, probably we couldn't separate it. This is actually just it's a public database for testing this type of methods. So for testing time series classification methods, and of course they have chosen dot motions which can be read out from the data.
okay, fair enough. So the other one is I also did a kind of
Yeah. Yes.
So thinking that it's really good.
Yeah.
But do you think this is then achieved by AI will never test or take over? Because well, in elements it can be something that human brain is doing, but not just between switching between system 1 and 2, but so it's not gonna happen. It's not that it's not gonna happen.
But I think that in this way that we pursue nowadays, the AI never will win as a general intelligence, never take over us. If we use a mixed system, so I think this is a new direction. So so far the classification task based tasks, we always build a system 1, and if we can give new tasks which leads the system towards more complex structures involving system 2, then I don't know. I cannot predict that how far it can lead. Maybe it would be a more intelligent general intelligence than we are. I don't know.
Okay, so I don't want to cut the discussion, but it's time to go to have a lunch. So let's thank Tony again. And, since yesterday, so please follow Balázs to proceed to the restaurant. And the very important thing, we put the last talk of the session in front of before the next session. So please be back at 1:40 when we will start. Okay, 1:40 to be in the S.
For example, like they now got a where it seems like they're trying to solve this. It's like we're looking at things as
Igen, itt van az átalakító, hogy megpróbáltuk. Hát ez lesz Robert, nem tudom, erről nem jött. Szerintem egyébként a kábelnek semmi baj.
Nem hiszem, már hiszem. Mert tegnap állítólag én ugye ebben nem vettem részt, tegnap már volt valami ezzel probléma, és akkor ezzel megvolt.
Ezzel
Mert
tippelgették.
meg automatikusan nyugodtan próbálj más sportot is enni, ezek ki vannak. Hát csak tegnap te voltál itt ezen a két helyen, ugye?
Igen, csak akkor nem én a gépet, nem ezt a gépet használtunk, hanem egy másikat.
Ja, értem.
És
De a portot ugyanazt.
igen, ez
Nem voltak hozzá az Ádámig, de mindjárt igazad. A sima VDC-VP, 5G-s is, és azon nem lesz senki. Lehet, hogy ez lesz a megoldás.
megelőző network beállításokat.
Ezzel elemet cserélek közben.
Ez standard volt.
No chance.
Ha akarsz,
Hát az iOS-en is túl sok közön nincsen. Úgyhogy lehet adaptát letiltani, visszahozni, vagy ilyesmi.
nem, hát elméletileg, hogyha arról folyik, mi akkor is nincsen mondjuk
Fogják
a
kell. Próbálj meg.
meg adresszéhez kötve, akkor
Másik pont. Ha tegnap az volt, ez nem romolhat el.
igen, én is azt hiszem, nincs jobb bedugva.
Szobadugva valahova. Itt is próbáltunk, mert is egy portot is van. Ezzel nem múlik. És akkor mi az én akkor az csak ez lesz majd. Ez lesz a megoldás. Ezt nem szeretnék.
Nem lehet, hogy valami specifikus, nem lehet, hogy statikus IP-re van állítva.
Nem használtunk kábel, igazából szerintem tegnap sem használtunk kábel. A videót.
Igen, a horror, vagy csak én ne hagyjam el. Gergő, mindenkinek véget vessek, vagy end for all, vagy csak én lídeljek?